All right, welcome back to week two in this course. Hopefully your week one went smoothly, had no problems with the lab or the lecture videos last time. You got an SPSS all set up. Today we are going to be talking about defining variables. So the overview of this week, first we're going to be talking about constructs and variables. What is a construct? What is a variable? These terms we're going to be using throughout the semester. Then we want to talk about why do behavioral researchers care about variability? And then what does it mean for a variable to be valid in this world? We're going to start introducing the concepts of validity. And then later on next week, we're going to be talking about reliability to follow up on it. So first, what is a construct? This is any kind of abstract, broad concept or topic of study. It is, in the basis, what is the researcher interested in? What is the phenomena that is being, categorized and discussed here? And this can have a very complex understanding. It's abstract, so it can have lots of different multiple parts. It is not directly observable. While we might have an idea in our head of what this construct might represent, the phenomenon in general can't be measured as such. So we might have things like love or intelligence, life satisfaction. Again, these are things that we have in our head as ideas of how it manifests, but they are still abstract. If we really think about, tell me what love is, it's going to be very challenging. Tell me what life satisfaction. Okay, I can give you somewhat of a description of it, of quality of life and joy, but what is quality of life? What is joy? These are big abstract concepts. So when we have a construct, we need to start boiling down what is the researcher actually trying to study. The first way we boil down and define one of these abstract ideas is through a conceptual definition. This is trying to be more precise about exactly what we are measuring. You might have an idea of the definition in your head as one researcher, but another researcher might have a slightly different definition. And so you are trying to establish for the person who is reading your research or using your research, what are you actually measuring or manipulating? So in this case, you might have aggressiveness. Here it's the definition: pursuing one's aims and interests forcefully, sometimes unduly so. All right, cool. Now we have an idea of what aggression is. Maybe somebody reading it, you thought aggression was something slightly different. Maybe they thought it was more like assertiveness or vigorousness. And so what you're doing is establishing how your construct differentiates from other similar but distinct constructs. What are you really trying to understand? Now, once we have an idea of what are we trying to understand on a broad, big picture of our construct, then we want to get more into the nitty-gritty of how are we observing or measuring this construct. That is called our operational definition. This is the specific way a construct will be manipulated or measured. So whereas the conceptual is what are we measuring, this is how are we measuring. And the process of taking that conceptual definition and turning it into something we can actually measure, that is called operationalization. And it's an important step in the measurement and for all researchers to take this big idea and turn it into something that we can actually collect data on. And this is going to help to inform what kind of measurement instrument or how we are going to actually assess and apply numbers to a behavior. So there's one study that was looking at aggression, and they thought there's multiple different ways. Or sorry, I shouldn't say one study. There's multiple studies that looked at aggression. One study just wanted to measure how many angry faces, the facial structure, how many times in a conflict does someone kind of lash out visually and non-verbally at the other person. And you could count the number of times. Or, I think this is a fun study, they did some interaction that was frustrating and then gave the participant an opportunity to clandestine, really secretively pour hot sauce into somebody's drink. And depending on how much hot sauce they put in the drink, determined how aggressive they were. If they were not very aggressive, they'd be just kind of nice and like, oh, here's a little dab. But if they're very aggressive, they say, yeah, take the whole bottle kind of thing. Interesting way to operationalize. Another one was just after you get into an incident, get bumped and somebody knocks into you, do you later hold the door for them or not hold the door? that kind of thing. So these are different ways of measuring what the researcher has defined as aggressiveness. And you can see that there's a lot of variation in how these are measured. Some of them you might think are good indicators. You say, yeah, I can see how that's aggressiveness. And some of them you think, all right, interesting, hot sauce, but cool, yeah, that could be an idea. I don't know. For me, maybe I think, oh, sriracha, it's delicious. Why not more sriracha? I'm being nice to this person. There's lots of different ways of operationalizing, and these different operationalizations have different validity, have different quality to them that we're going to be talking about in this course and how to assess those. So let's do another example. How about intelligence? So we have a conceptual definition of intelligence. You think for a second, what is intelligence? How would I define it? Well, I'm going to give you my definition, or the one I looked up at some point. This is the capacity for abstract thought, understanding, communication, reasoning, learning, planning, and problem solving. Whew. That is a mouthful, and there is a lot to get through there. All right, so this is fine, but how does a researcher use this? Again, that's where we have to do our operational definition. The operational definition might be different ways of measuring somebody's ability to problem solve. For instance, a lot of studies that I've seen have used what's called a Raven's progressive matrices test. So this is a test where you just have to fill in kind of the missing space in the bottom corner. So you would look at this and think, oh, okay, so the top row has all squares, and the black square, the black segment is rotating clockwise to the bottom corner. All right, cool. The middle row has circles, and the black square, the black portion is rotating clockwise. And then you have the bottom is, oh, it looks like there's two diamonds. So my inference is that there'd be another diamond, and oh, it looks like it's rotating too. So my inference would be that the black portion is going to be on the rightmost section of that diamond in the bottom. All right, cool. If you got that right, you'd get 1 point, because that is what it is. It's a diamond with the black portion in the rightmost. So you get a point. And that's one way of understanding intelligence. And these might be easier or harder. For instance, here's one from the Raven's progressive matrices. And for those of you who really care, give you a second to pause here and see if you can figure it out. Maybe some point I'll put an Easter egg of what's the actual answer. But maybe you've never heard of the Raven's progressive matrices, but I bet you have heard of an IQ test. And that's what the Wechsler's Adult Intelligence Scale is. That's the fancy name for what we know as the IQ test, which is a specially formulated test that fits a normative scale. It asks particular questions. Normative being a normal curve, so a lot of people are kind of scoring the same score around 100, and then the people who are further out, either lower or higher, can kind of, we know the percentage of the population that fits that. So only 2% of the population have scores above 130. So this is another way. But the Raven's progressive matrices, maybe that's really good for people who are good at this kind of problem solving, maybe mathematical minds, but does it really represent all intelligence? In the IQ test, it has very specific questions, but some of the context and clues we know from the IQ test are really conceptual and cultural based, that by knowing kind of the context of the question, it can help you to answer. And we found that when we apply the IQ test in other cross-cultural analyses, the normative nature of it kind of alters. So while these are two ways of measuring a concept, they're not the only ways. So operational definitions aren't the only way, and they aren't always perfect. They might not accurately capture the intended construct. Again, whether it's a different culture, or we have found out through studies of, quote unquote intelligence, that there's lots of different versions of intelligence, lots of different types. So that logical mathematical might be really good at the Raven's matrices, but someone who has a linguistic or a naturalist or an interpersonal intelligence might not find that those are that easy to accomplish, but they are still intelligent people. It's just the way we are measuring it is not quite capturing their intelligence. So how we operationalize is a very important step for all researchers, and part of research is operationalizing the same construct in different ways. Now, before I go more into how we are operationalizing and the process of evaluating the operationalized constructs and definitions, I want to introduce to a term that we're going to use a lot. That's variables. When you operationalize a construct, you develop that operational definition that is creating a variable. That's all it is. A variable is anything that has the ability to vary or change. It has different levels. You can be happy or sad. You can have good sleep or bad sleep. You could be a freshman, sophomore, junior, senior, these different levels of your education. And how we measure these, it dictates whether they are continuous or categorical. I talked in the lab about age as a variable, as a continuous versus categorical, that while there are specific levels that we kind of think about in our society of different ages, I'm 19, 20, 21, really it could also be thought of as a continuous variable, that there's kind of this amorphous flow between them, and there's no real difference between there is a difference between one 19-year-old and another on so many different factors that the just age is just a number concept. So we treat it as this kind of continuous flowing value. We also might not want to say good sleep versus bad sleep. A categorical variable has to draw a very distinct line between the two levels. And where's that line between good and bad? So we might want to make it more of a continuous of I had really great sleep versus just okay sleep versus just not so good sleep versus really bad sleep. Create that continuous value. We do this a lot with subjective happiness, quality of life as well. It's not necessarily having a great life versus a terrible life. There's a lot of nuance in there for a continuous variable. However, there's a lot of other variables that we have very clear demarcations behind. So freshman versus sophomore is dictated by your credits that you have at an institution. So there's very clear lines, and we can draw a difference between people based on the category they are in that variable. And the idea behind a variable is that individuals can shift between these. Sometimes people can have good sleep and sometimes they can have bad sleep. Sometimes they're happy, sometimes they're sad. Sometimes they're freshmen, sometimes they become seniors over time. There's some influence, there's some variation that is happening. Now, while a variable is anything that can vary, there are some variables that in our specific study don't vary, and those are known as constants. So if we are doing an analysis of happiness levels across college campuses, and we have different college campuses, that college campus could be a variable because some people are at ODU, some people are George Mason, some people at VCU. And so it is varying. People have different levels, different categories of that variable. But if I was to do a study of happiness at VCU, well, technically institution is something that could vary, but in the study I am doing where I'm only collecting VCU students, it no longer can vary. It's now a constant. And so it's not going to be as useful to me because everybody in my sample has the same score. So we are trying to look for the constants and not measure those constants, or not really focus on those constants. Know that they could change, but they happen to not. This is important, especially when you're looking at demographic variables. So if I am studying a population and I think I'm representing the variability or the amount that can change in my population, but then I look at my demographics and see, oh, I only have men in my study, that constant of the gender, of male gender, suddenly makes my interpretability a little bit more nuanced, let's say. If I only have our white, industrialized, well-educated, we're going to talk about these weird samples, and nothing is varying in that demographic, that's going to become a constant and it's going to change our interpretability. So be watching out for those things in your studies that might seem like they can vary, but don't actually in the data that you collected. All right, so that's the difference between a constant and a variable. But now let's talk about how we use the variables. Every research question is trying to understand the relationship between one variable and another. We're going to, for right now, call it x and y. What is the relationship between variable 1 and variable 2? And we don't always know the relationship or the direction of this relationship. We might see that there is a relationship, but we can't necessarily interpret causation. For instance, is studying related to school performance? We might find and think in our heads, okay, I collect the variability in X and the variability in Y, and I see that there's some relationship between those variability. So maybe people who study more do better at school. Okay, that's one interpretation. But it could also be that people who do well at school are just intrinsically motivated to read more, or maybe extrinsically they're getting good grades and they're thinking, oh, hey, I must be good at this. I should go do more just on my free time. So the relationship is unclear, and as behavioral scientists, we are trying to explore those variable relationships. Now, I can call these X and Y, but we're going to start using different terms for X and Y to be a little bit less confusing. We are going to talk about independent and dependent variables instead. So when I said X, I was really talking about that first variable, that independent variable. Our IV is thought of as a predictor variable. I just spent a while talking about how causation is a little bit confusing, so we need to take this with tongue in cheek. That when we are thinking about our study, we are kind of coming into it with a mental idea that one variable is an influencer. Right? This IV, independent variable, is potentially the cause of the outcome, which is going to be, spoiler alert, the DV, the dependent variable. In a true experiment, the independent variable is completely manipulated by the experimenter. They are the ones who are causing, the experimenter is causing the IV, which is then trickling down and having an effect on the DV. But in observational or correlational studies, we can just say a predictor variable, that we think that this variable is somehow cueing information about or predicting information about the dependent variable. And this IV could run a gambit of different variables. You could look at categorical variables like freshman, sophomore, junior, senior. You could look at the continuous variables like good sleep, bad sleep. And some of these you might be able to manipulate or not. Variables, demographic variables like your college year, not so manipulable, right? The kind of people are that. When you do a study, you can't just suddenly change somebody from being a sophomore to a junior. But other variables you can. So sleep might be something you don't manipulate. You just ask people, how did you sleep last night? Whereas some researchers will very intentionally go through lots and lots of means to manipulate sleep by creating really good, healthy sleep environments and sleep behaviors and comfy pillows and good sound machines or non-sound machines versus bad sleep where they wake you up every few minutes so you're never getting into REM cycle. So researchers can manipulate some variables. And when we're designing our IV as researchers, we're always thinking about how much control do we have over that IV? How much can the researchers actually control which group the participant is in? And that's what the manipulation is. All right, so that's a lot about IV. Now the DV. The dependent variable, the DV, is this variable that is potentially being influenced by the IV. This is sometimes noted as a Y variable or an outcome response variable. But again, this is the kind of conceptually, the independent variable is having some effect or influence potentially on the IV. And this dependent variable is always a measured, observed variable. The idea being that the researcher doesn't want to manipulate the DV. The researcher wants the IV to manipulate the DV. Again, the researcher wants the independent variable to be the thing that is manipulating the DV. So we can have a number of different ways of a number of different dependent variables. We could have life satisfaction, happiness, whatever you want to, whatever you get out of this picture here. Or we could have things like sleep. So maybe depending on your level, your student level, it changes how good or bad sleep you have based on for reasons. And every research study is trying to establish an IV and a DV and a relationship between. But of course, we talked about last week, we know that the relationship between these isn't always a direct one. Sometimes we have other variables that are explaining it. We have these confounds. We have a moderator or a mediator that is influencing the relationship. But the researchers need to start out with the idea that one variable is somehow related to the other, and then from there we can explore that relationship. All right, so we got a lot about IVs, we got a lot about DVs, we know what a construct is, we know how we're creating these variables and when to make sure that the variable actually varies, it's not just a constant. But why do we want that variability? And that's the next section here. Variability is fundamental. So first of all, variability is how much people are different. And people might differ based on the situation or the individual, or the same individual might be different over time. So here on the example, we have risk taking, or let's say in this situation, just how much you enjoy the idea of lead climbing up a big rock face. Some people might see this and get a little clenched up. Oh, that doesn't look like fun. Whereas other people say, oh, that is my dream day. Why am I watching these videos? I could be rock climbing. And then there's a lot of people who are in this middle saying, oh, yeah, okay, that might be cool, but I don't know. I have other things I want to do. So different people have different feelings, might have different situations. Like if you just came back from some really exciting trip, you might think, oh, that was so invigorating. I want to do something else like it. Or maybe you're someone who used to like this kind of stuff and doesn't now, or vice versa. You used to be really risk averse, but now you're kind of seeing, hey, maybe there's more out there that I could be doing and trying out. So variability, everybody has variation in these behaviors, these thoughts, feelings, and behaviors. This variability in situations and individual and across time is what behavioral scientists are interested in. Psychologists and behavioral scientists in general are trying to study that variability in order to understand how and why there is this variation. So, for instance, what aspects of the situation cause the differences? Are the same people different in different situations? Or vice versa, do different people act differently in similar situations? Is there something between people that matters? And then why might there be change over time in these behaviors, variation within the individual? All of these are different aspects of variability that behavioral scientists really want to understand and is part of our research. All questions that researchers in behavioral scientists are asking are related to these variations in behavioral variability. So our examples that we've talked about, performance increases while being observed, that social facilitation that we learned about in last lecture. Or maybe we're seeing variation in maturity and we might see that that's related to variation in age. Does getting older make us more mature? Or there's different types of therapy that could be introduced into a family interaction, and of course there's variation in family interaction. So how is the type of therapy and the variability in that related to the variability and the patterns within the family? All this is variation responding to variation. With all of this variation, researchers are trying to measure it. A lot of research and a lot of what we're going to be talking about in this course is how to create those operational definitions of variables so that we can measure that observed behavioral variability. But as we saw, not all variables, not all operationalized definitions are perfect. So what we're trying to do as researchers is eliminate the flawed aspects of the studies. What is it about the way we are measuring things, and the way we're measuring this variability, that is introducing error, that is not quite gathering the actual phenomenon? So we're trying to assess the benefits, the great interpretations, but also how to increase that validity and reliability, which is stuff we're going to be talking about a lot today and next week. So things like add a smidgen and a dollop and a pinch, well, what do those mean? Those are confusing. Those aren't good definitions. We are trying to improve that so that when we measure variability, we know exactly what we are measuring. And in this measurement process, we are going to use numbers. Measurement of behavior involves the assessment of this variability, and we are going to assign numbers to those variability. It's like taking a ruler and putting it on the psychological phenomenon, behavioral phenomenon we care about. Variability in numbers reflects the variability in behavior. If it doesn't, if there's no change in the number, there's no change in the level of our variable, if the behavior changed, then it's really a worthless measurement tool. If stuff is changing and our tool isn't picking up that it's changing, what's even the point? For example, we might measure depression level, and if somebody is feeling more depression, our scale should show that they are measuring that they are experiencing more depression or less depression. With IQ, we want to make sure we are accurately assigning a number. So if there is someone who fits this construct of intelligence better, we want to have a higher score for that individual. And if we have come up with a metric like the Ravens that is really good at measuring one type of IQ or intelligence, but not others, well, sometimes someone who is more intelligent in maybe that interpersonal, there won't be movement on our Ravens matrices measurement tool, in which case the measurement tool isn't as valid, or maybe I won't call it worthless, but isn't as useful. Heart rate. This is one that we have a pretty good measurement tool for. We can measure how fast our heart is beating, but this hasn't always been. We could try it with your fingers and put it up against your neck and measure, and there might be some measurement error. Maybe you're not counting at the right speed, or you don't have a watch to know exactly it's been a minute. So we need to make sure that as we are coming up with these operational definitions, we also have a good measurement tool assigned to it. Once we have those numbers, then we can begin with our statistical analyses, where we describe and account for the variability in the data by assigning different measures of variability, and how is variability in one set of data related to variability in another, or on one variable related to another variable. And by looking at the relationship between these variables and their variability, we can maybe develop an idea of prediction or causation depending on how we have designed our methods and our research study. Okay, so that was a lot about variables and why variability and operational definitions. So you had a lot of terms so far, a lot of definitions, but hopefully you're just getting the idea that change between individuals is important, and we are measuring that, and we are quantifying it, and then we are analyzing it. So part of the analysis, we're going to look at numbers. So this next section, we are going to have some math that you're going to see. So for those of you who want to, this is a good place to pause, take a break, go get some water, get a snack, and then come back when you're ready. We're going to talk some statistics about, statistics. All right. So let's go into our example. There's going to be a little bit of math in here, but it won't be too much. This is not a math-heavy course, but you do have to have an understanding of the variation and comparisons of variation. So let's start with an example scenario. Let's say that you just took a bio quiz and you earned a 16 out of 20. And I ask, how did you do? Well, you know that you could have got a 20, maybe. But what is a 16 in that context? Is that a good score? Is that bad? You don't really know, because for any score, you need to have some kind of comparison. Maybe you want to know, what did you do on the last quiz? So there's some time change in that variation. Maybe you know that 8 out of 12 students earned a perfect 20, so you are in the minority and didn't get the perfect score when a lot of other people did. Or maybe it's the opposite, where the class average was a 12, which is below your score, so you did better than average than most people. So the teacher may present some descriptive statistics or graphics of the class scores so that you can have this comparison to work with. You can see how your score related to others. And that's what researchers are doing. We are looking at data and comparing it against others for context. And there's different ways of looking at the context. Let's say there's 12 students in this class, a pretty small sample size, and you get to see it. Well, there's your score of 16 in the midst, and with a small sample size like this, you can kind of eyeball the scores and see where you stand. You say, oh, I see some scores that are higher than me, I see some scores that are lower, okay, I'm kind of in the middle, that's great. And this is possible because there's a small sample, but what if there's a lot of students? What if there's 125 students, or 200, or 1,000 people? Well, it's going to be a lot harder. And so that's why we need to create these data sets where we summarize the descriptive statistics from that data. We can't look at every raw piece of data, so we need to look at the overall impression of the data. That overall impression of the data is going to come in two major ways, and that's through our measures of central tendency and our measure of dispersion. This is a place where you might suddenly think about your statistic notes and go, hey, I remember these concepts. They were very important in the statistics course. You're absolutely right. They are the central point of our statistics classes, learning how to use central tendency and dispersion to infer things about our sample. So the three measures of central tendency are going to be our mean, median, and mode, and those are a single number that are describing the entire kind of the midpoints of the that central point of the data. Or you could have your dispersion, your variability, that's the range, variance, and standard deviation, which indicate the spread of the entire data set. First, just mentioned inferential statistics. So inferential is when we take a small sample and we infer something about the population. This is when we're trying to talk about the representation, that if we find some information, some mean, some range on our sample, we like to be able to say it represents the whole population, which is everybody who are similar to that sample. And part of research is figuring out how likely it is that the variability that happened in our sample is because of the measurement and is because of something about that sample or variables that are influencing that sample versus error and random noise that's occurring. And which statistical method you use depends on your type of data and your goal. So throughout the semester, we're going to start talking about different kinds of analyses, but you could also go back to your statistics notes and look through when do you use a correlation versus a t-test versus an ANOVA. Right, but all of it is inferential. We're taking a small subset and we are relating it to some inference about the population. We are understanding the variability in a sample and interpreting some variability in the population. Okay, but here's the math. So we're going to start off easy. The measures of central tendency of a mean. This is also known as an average, but in statistics we like to talk about it as a mean. A mean is simply taking the sum of all scores divided by the total number of scores. In statistical notation, this is represented as that x bar, it's the x with the bar over it, which equals the sum of x. Sum here is represented by that sigma, the capital sigma, which looks like a big Greek E, and that means take all of the x values and put them together. And then you divide by n, which is the number of pieces of data you had in the data set. So here we have 12 pieces of data, we sum them all up, 14 plus 8, etc., and then we divide it by 12, which is the number of pieces of data, we get 14.83. That is kind of a central point in the data set here, and so you could say, hey, my 16 is above that mean, so I am doing better than average. I'm doing better than kind of the representative score. However, this isn't always the best way of measuring central tendency because it's very susceptible to outliers. Let's say most of the class scored very low score, but you have a few outliers who scored really high. Or in this case, you actually have an outlier of that 9 or that 8 points there. Above them, the lowest is a 12 point, so that's a 4-point sudden drop. So that 8 point, that low score, the person who showed up a little tired and hadn't really studied and isn't good at tests, really brought down the average. So maybe the other 11 participants, if you'd done a different mean, you might have had a very different average. And so those outliers can kind of skew the mean in one direction or another. You might remember that term skew is when you have outliers. So another version of the central tendency that kind of gets in the way, it ignores those outliers, is the median. This is when you order all of the scores in ordinal values, and then you find the midpoint. And the midpoint is just the n plus 1 divided by 2. So in this case, you have n is 12. There's 12 pieces of data. Plus 1 is 13. Divided by 2 is 6.5. So you would order them, go down the ranks, and at that 6.5, right between number 6, the 6th position, and the 7th position, between that 14 and 15, that's the median score, the median representation of how well people are doing. And what you see here is that 8 is kind of, yes, it's a piece of data. It is a participant, but the value of that 8 isn't being represented in the median. So this midpoint of 14.5 is supposed to be a better representation. And you can see again that your 16 is a little bit above that. But this also has problems because maybe the midpoint is kind of like there's a lot of people who are below. It could have been 8, 8, 8, 8, 8, 14, 15, 16, 17, etc. So just ordering it doesn't always do anything. sometimes we want to know what is the most frequently occurring score, and this is the mode. The mode is here 12. You can see that that is true because it has 3 people who scored a 12. So that's much lower than that 14.5 or the 14.8, but it's kind of showing most people are getting a 12 on this. So you're 16, pretty good. Problem with this is that that increase of just one extra participant who scored a 12 really skews the data. There were still 2 people who scored a 20 and 2 people who scored a 16, so that's pretty close to the 3 people who scored a 12. So particularly when you have small data sets, those modes can be very distracting. So you don't want to put everything into that mode either. Really, when you're doing central tendency, you want to look at all 3. You want to look at the mean, the median, and the mode and see how they compare. Here you'll see that the 14.8, the 14.5 look very similar, but that mode maybe not the best representation of the data, again, because it's a small sample. But the median and the median, the mean and median are pretty close to each other, and regardless, your score of 16 is higher than both of those. So in the context of this sample, you can think that my 16 actually pretty good, as evidenced by this central tendency. Okay, so these central tendency are a single indicator of the population. They are that central point that's aggregating everything. But what it doesn't represent is the span of possible scores. It doesn't represent the fact that there could be outliers, or maybe there's a lot more dispersion where a lot of people are scoring the same in the center, but not so much on the ends. So we're going to look at this measures of dispersion as well. The first is the range. The range is just the minimum minus the maximum. So here it is the maximum score of 20 minus that minimum score of 8, a range of 12. On a 20-point scale, a range of 12 seems fairly large. So some students are in that perfect 20, while at least one missed more than half of them. Again, that outlier with the 8. So you're somewhere in the middle there. Right, so you now have a little bit more context that you're in the middle of the pack. That's pretty good. Right? You don't want to be at the bottom end. You want to be kind of higher. But range is very finicky. It does have some outliers. If you have one person who scored a 1 who didn't show up, or a 0, just didn't show up for the exam, that's going to really affect your range. Also, depending on how the scores are dispersed, your range could look the same. Here we see some disadvantages in the data set. This is anxiety score. So these 2 data sets, they have the same range, but clearly very different amounts of variability. In the first one, the anxiety scores are on a normal curve. You have some people who are very low anxiety, very high anxiety, but most people are somewhere in the middle, versus your other range where you have some people who are very low, but most people are pretty high anxiety. Both of those have people at both ends of a 1 and a 10, and so it's a 9-point difference. Same range, but very different representation. So that's why it's important to go on to our next measure of dispersion, which is variance. Variance is used extremely commonly. You can see that variable, varying. This is a common statistical representation that we're going to use in any kind of statistical test we do. So the variance is the degree to which the scores deviate from the mean, how much they are different from the mean. It's represented by this formula here of S squared, that's variance. That's variance for a sample. If you're doing a population, you'll do sigma, which looks like that fancy O, the Greek O. But in a sample, it's that S squared. And what it does is equal the sum of each of the scores, that's X, minus the mean. Remember, we saw mean is that X bar, and we've seen that sigma, the big Greek E, as the sum. So you take all of those scores and you subtract them from the mean, you get the difference from the mean, and then we're going to square it for reasons I'll explain in a second. Sum all of those differences and then divide it in a sample by n minus 1. Just as an aside, if you're doing a population, it's divided by n, but that's probably more than you need for this course. That's more of a statistics thing. But this is a sample variance score. For those of you who really like numbers and like seeing it, I'm not going to spend a lot of time on this slide, but you can see the process of calculating that variance. The leftmost column is the scores, those 12 scores. Then the column next to it is the scores minus the mean. So the mean, again, was a 14.8. We calculated that before. So the score of 8 minus 14.8 is a 6.8. If you look at your score of 16, you subtract 14.8, you get a 1.2. So all of those are just subtracting, is the difference from the mean, that individual score's difference from the mean. And then we square it. And the reason we do this is because if we don't, all of those differences are going to sum up to 0, and that's a pretty useless number for us to use in any kind of math. So statisticians have realized if you square it, you're good to go. So we square all of them. That 6.8 squared is a 46.6. The 1.2 for your 16 score is 1.2 times 1.2 is 1.4. You do that for all of them, and then you add them up, and that makes the sum of squares. In this case, the sum of squares is that 145.7. And the equation was to take the sum of those squares and divide it by n minus 1, in this case 11, because there were 12 pieces of data, and you get a variance, that s squared, of 13.2. A lot of math, and some of you are looking at this and a little overwhelmed, but it's just subtraction, squaring, and addition. And then you get that variance. And luckily, we have SPSS to do most of that for us, but we still kind of conceptually know that it is a sum of the differences. So we get this variance, which is representing the spread here. And we can go one step further by taking a standard deviation. This is where we undo that squaredness, the squaring the difference, by taking a square root. So we'll take that 13.2 and square root it to get a 3.6. What this standard deviation does is it represents the amount, every one standard deviation away is that many points. So if you had a 16, if you had an average score of the 14.8, it's saying most people within a standard deviation are within 3.6 of that 14.8. So we take 14.8, we add 3.6, and we get that 18.4. If we take that 14.8 mean and we subtract 3.6, we get the 11.2. All right. Again, that is heavy math that I just got into. That is your statistics course. I want you to kind of get a refresher on this standard deviation and how is it measured. But we are going to do most of the calculations in SPSS. I just want you to have in the back of your mind why this matters, why we care about dispersion, and when you see standard deviation, what does it kind of mean? If you have a bigger standard deviation number, it means there's greater spread in your variable. If you have smaller standard deviation, that means there's less spread. In other words, most people score the same score. So the standard deviation tells you, like, okay, if it was a 14.8, that's cool, I'm above it, but did most people score a 14.8, or was there a lot of change? And we can see there's a pretty big range in the standard deviation. Most people fell between a 11.23 and an 18.43. So you are in that, so you are like most. You are scoring similar to most other people. Pat yourself on the back, you can feel pretty good about that. All right, you made it. You just got through the statistics, that quick refresher, and that's probably, we're going to do some more in our lab talking about these measures, but this is your first reintroduction to statistics. You got those central tendency, mean, median, and mode, and you got the dispersion, range, variance, and standard deviation. So now that we've gotten that statistics refresher, let's go back to talking about variability and variance. So the total variability in the behavior is made up of two parts. And I mentioned these earlier with researchers are trying to make sure that what they are measuring is representative and that the variability is being picked up in their measurement tool. Because there's two types of variability. The first is the systematic variance, and the second is error variance. Systematic variance is how much of the variability is related to that independent variable in an orderly and predictable manner. That means that depending on what's happening in the IV, depending on what manipulation has happened to the participants, or depending on their demographic characteristics that you are not manipulating, you are just measuring, everybody within a certain level of that IV are kind of predictably and orderly getting different scores, varying in their scores on the DV in the same way. So in this example, we might expect that those who took the practice test, maybe that's a measured value of did you take the practice test or not, we predict that the people who took that practice test are going to score higher on the bio quiz. If that is true, that's great. That's systematic variance. But life isn't so easy. We do see that sometimes people score high for other reasons, or they score low. So here's error variance. Error variance is that variability in behavior that is just random. There is no systematic nature to it. There's no predictable form. It's just stuff's happening. So there's that one person who skipped breakfast, or the one person who's retaking the course has already seen the questions or already dealt with the concepts and seen where they struggled, or the person who's just feeling sick that day or went out to party last night. These are things we can't measure. They weren't under we didn't measure them in our IV. We didn't think to. Now, some of these we could decide to measure. We could measure how late were you up last night as an independent variable, but we would have had to have thought of that before we did our research, because if we don't measure it, we can't know, and we can't do it after the fact. So when we are designing our research, we are hoping that we are collecting the systematic variance that's happening. We're thinking of the variables that might be systematically affecting our outcome, and we are hoping that there is less noise and less error in the variance we're collecting. Now, I say hope, you just got to accept that there is always going to be a lot of error. No study is perfect. We are simply trying to develop better methods and better experiments so that the error is accounted for, or that we have enough participants that the error starts to disappear. So once again, restating, more error variance than systematic variance means we have more difficulty determining the relationship between our variables. Going back to the IV and DV, that independent variable we think is going to be related to the dependent variable. But if we have a lot of error variance, not systematic, but error variance, then we can't really interpret that relationship. So as researchers, again, we are trying to develop studies that account for the error variance, reduce it, and are able to identify systematic variance. And the systematic variance is what's discussed in our research studies. And so we need to have the differences in our results. They're coming from where? We're going to use statistics to do that. And this is when we have our effect sizes. Effect sizes are indicating the size of the relationship between two variables, or the size between two different groups. So this is basically taking that systematic variance and telling us how much does the systematic variance outweigh the error variance. It is the proportion of the systematic variance out of the total variance, the amount of change that's occurring, how much of it was due to our independent variable. If we have a lot of error, that means we're going to have very little systematic variance, and so our effect size will be very small. It's saying that the amount of variability explained by our IV, the amount of variability in the dependent variable explained by the independent variable is very small. But if we are noticing that as one variable changes, the other changes in very systematic ways, there's a lot of systematic variance, that's going to account for a lot of that total variance. We're going to have a bigger numerator, and we're going to have a larger effect size. The effect size in this way is always a proportion, and so because it's proportional, we can compare it to other effect sizes. And this is what researchers do. When we have multiple studies, we can look at the effect sizes in one study versus another, different ways of operationalizing a study or coming up with constructs related to the variables of interest for a specific hypothesis or a specific theory. We can look at those different kinds of effect sizes to understand the different systematic variation, and then we can do a meta-analysis. A meta-analysis is when you take all of the different studies out there and you do some fancy math to aggregate all of those effect sizes, bring them together. So it's a special procedure that examines every study about a particular topic to assess the relationship between these variables. It's really important here to say, and I've said it a few times in this course, no one study is perfect. No one study is true. There's always error, But some studies have less error. Some studies have more error. Some studies are looking at a variable in a unique way that might introduce more error, but come up with a better, a more valid representation of the phenomenon. Whatever it is, every study is unique, and every study needs to be looked at and brought together in these meta-analyses. So a meta-analysis collects all the effect sizes and it averages them together through some fancy math to give a comprehensive estimate of what is the relationship between the variation in these variabilities. All right, one more time. Behavioral scientists are trying to understand how and why the behavior varies. We established that variation matters, and we're trying to see how the variation in one variable is related to variation in others, be that time or the individual comparing to others or the situation. We want to understand that variation. We need to collect information about that variation. So as researchers, we are collecting data that represents the behaviors, and we hope to see variation in the data that we collect. We then examine the data using statistical methods to look at that variability, and we want to identify the systematic variation, not so much the error. We want to account for as much systematic variation as possible. And then once we have conducted the research on our own, other researchers are conducting similar studies, and we can pull it all together to run those meta-analyses across different studies. All right. Well, next question though. How do we know that we're collecting what we want to collect? How do we know that we are accurately measuring the behavior that we are discussing, accurately measuring our construct? And that's what we're going to talk about next. And the last section of today's video is validity. How do we know we are accurately measuring a behavior? So I've kind of dropped this term in a few times today just to get you familiar. Oh, what's that validity term? Validity is the relative accuracy of a conclusion. It's how correct is this statement? How correct is this construct or this operational definition? Is this measure that I have really reflecting what I want it to be reflecting? And how does it capture what it's really like in the real world? It's like an identification card that's saying, yes, this is in fact the thing you are trying to measure. For example, maybe I'm trying to study belief and trust in medical science. There could be multiple ways of measuring this, and there might be two separate studies out there measuring in different ways. One of those studies might measure it based on whether you're getting vaccines, with the idea being that variation in how much we trust medical science might lead to variation in how likely the person is to get a vaccination versus not get a vaccination. Theory being that greater trust in medical science will lead to belief that vaccines are good and are useful to society. Whereas another researcher might say, all right, let me measure the amount that people are wearing masks. Again, with the belief that people are varying in the level that they are wearing masks, maybe due to their belief that COVID can be spread through, and other diseases can be spread through unfiltered respiration. Both of these could be ways of measuring this health, this construct of belief. But you might be looking at this and thinking, there might be other explanations for this. There might be other reasons that someone would get a shot, or other reasons someone may or may not wear a mask. There might be extra variation in the behavior that isn't actually representative of trust in medical science. And that's what validity is. We are trying to create metrics that are more representative, that there is not this extra error variation in people's behavior that does not represent the construct that we're trying to operationalize. Here's another example. Maybe we're doing a stress study. We're trying to measure stress. And so one researcher gives a math test. Easy, simple. Some of you, after the past few slides, you can definitely feel, oh yeah, not really liking the math. It's kind of stressing me out. Well, that's one way of studying it. Or you could do some research like I actually did in grad school, where you bring people in front of a panel of judges who are all sitting there staring at you with a video camera while you stand there with no notes, and they ask you to recite math problems, subtract 7 from 1112, and go faster, faster, faster. You got to do your math fast. You got to do it. You got to do it. One of these may be more stressful than the other. Yeah, that math test you might not enjoy, but you'll make it through. Whereas the interview, it's called a Trier stress task. Oh gosh, that is stressful. And as researchers, we actually use that second one, that Trier stress task, as a way of manipulating stress. It is shown to be a pretty valid way to create stress. In fact, you can do this and then measure people's cortisol, which is a hormone, a stress hormone in your body, and you will see spikes in that stress hormone when people come in this. Whereas a math test, oh, you might be a little flustered, but it's not quite a valid measure, a valid manipulation of validity. So when we are operationalizing, we should think about, am I measuring what I want to, and does this capture what life is like in the real world? Now, that real world is very important here because you also, while something might cause the stress response or might cause and manipulate your variable, your construct, maybe it doesn't happen in the real world. How often do you stand in front of people and give a math interview? Well, okay, so that loses some validity there too. So we're going to talk about those different ways we can assess validity. Another way to think about validity here, just real quick, is the dartboard. That if our construct, the perfect representation of our construct is that center bullseye, the measures we are using are trying to get closer to that bullseye. And something that's just measuring something wildly different, it's out there on the white, that is going to have low validity. Something that is getting really close to the center and measuring it correctly, that is our high validity. And we are trying to create measures that are getting closer to the true phenomenon, the true construct. So as you think of validity, you can think of more or less valid measures. For instance, a yardstick is a pretty valid measure of your height. You stand up, you hold a yardstick, you can tell exactly how tall you are. And a lot of that is because we have systematically created yardsticks to always have the same information of an inch is an inch, a yard is a yard. If every ruler you got was a kind of different length and different spacing between the ticks, it wouldn't be a very valid measure. But because all yardsticks are the same, we can measure that height. But you would never use a yardstick to measure intelligence. That wouldn't make any sense. They're just unrelated constructs. But sometimes it's not so clear, like personality. Many of you have probably taken what's known as the Myers-Briggs exam, the Myers-Briggs type inventory. So you'll see this INFP and the ENFJ. You might know your type. Maybe you took it in an intro class. This is an old way of measuring personality, but research has shown that it's actually not a very good way of measuring personality. There's a lot of inter-individual change that you took it a long time ago, you might be different now, so is it actually your personality? It's also very susceptible to different populations. It's very susceptible to bias in the responding. You can respond how you want to, not necessarily how you are. But instead, researchers have constructed what's known as the Big Five inventory, the BFI, which is isolated personality down to about 5 factors: your extroversion, neuroticism, agreeableness, openness, and conscientiousness. And we found that that is a much better, more valid representation of personality than any of these other type indicators. So how do researchers assess more valid versus less valid? How do we come to the conclusion that the Big Five inventory is more valid than the Myers-Briggs? Well, the first type of validity we're going to look at is construct validity, which is a much broader concept that we're going to talk about next week as well. But on its base level, it is just how well did the researcher operationalize, develop each variable? Does the variable represent the real construct? So if I'm a researcher who's trying to study stress, I want to create stress in an individual so that then I can see how they cope with it, or I can see if there's other ways I can manipulate them coming down off of that stress, or how long the stress lasts. I do want to manipulate stress, and I need to come up with a operationalized way to create that stress. And so I need to ask myself, what are the different methods out there? I could give them a small math task, or I could give them that Trier social stress task. And I want to see, does it elicit real stress? And through research and manipulation, I will find out whether or not people actually feel stressed in this, and there's different ways of triangulating that. As another example, let's say that I'm trying to understand how attractiveness plays into people's perceptions of others. Do you think people who are more or less attractive are more likable, or more neurotic, or more Machiavellian? And so I need to manipulate attractiveness. And so here I might have two pictures, and I need to know, is this a good indicator of variation in attractiveness? Would people generally lean towards one versus the other as more attractive or less attractive? And you can look at this and think, okay, there might be some construct validity to that. But I bring up this example here particularly because there's some issue with this sample. And that has a lot to do with external validity. This is how well do the results generalize to represent other people or contexts. So in that last example of the two faces, you might notice that they are both Caucasian. So how is attractiveness interpreted different in non-Caucasian populations? So we got to think about, is there different contexts when people are going to assess something different? Are you going to assess attractiveness more if you're just sitting on a bench watching people? Are you going to have a different idea of what is attractive? If you're in an interview and you're putting on your best face and you're thought of what is attractive in an interview versus not in an interview? What about on a date? Are there certain things that make somebody more attractive than just how they look? Maybe it's how they behave. So these actual real life situations, that's the external validity. Just showing someone two faces on a computer screen might not always be the best externalization. Same thing with the Trier social stress task. If someone is getting stressed during that situation, that's also a very unique phenomenon that they're in. And so it loses a little bit of that external validity. Again, any kind of study we do where people are just sitting in front of a screen is going to lose some of that external validity. Whereas if you are out there in the real world observing people who are going about their day-to-day, living in the real world, then you're going to have very high external validity. Only problem with that is you lose a lot of your ability to manipulate. When you are in a controlled experimental room, you can control for a lot of that systematic variance, reduce some of the error variance, because all of the variation that's happening around you is being controlled. And we're going to talk a lot about controls and how to improve your external validity in a study to make it feel more, to get more control, which loses your external validity, but you increase the construct validity. Another term when discussing external validity is going to be this generalizability, the degree to which we can take the findings from a study and apply it to other populations. We can generalize to other people or contexts. So people is a big example. I've already kind of mentioned it, but these weird samples. So this is your Western, educated, industrialized, rich, democratic. We know that much of psychology over the past many, many decades, in fact, most of the history of psychology, the main samples that are being studied are from this weird sample. And so a lot of what we think we know about the way humans work isn't really how humans work, it's how weird people work. And as we are becoming more and more aware of that, this cross-cultural research or trying to get wider samples that represent non-weird samples, wider samples, the more representative of the human condition, is going to be very important. Until then, we have to take everything with a grain of salt. It has past research has low external validity in terms of that generalization to the broader human condition. We also want to know that there's generalizability across situations. So if you are in a study and you're filming people and you're standing them in front of a panel and you're seeing that they're stressed or they're fighting, well, would they act similarly if you weren't videotaping them? So can we create situations where the external validity is increased because people don't necessarily know that they're being observed, or they would act the same way in the lab that they would act outside of the lab? You're making it more consistent across the lab versus non-lab. That's how you can increase that external validity. Again, we'll talk about how to do those when we get into research, the really experimental research methods. So that's kind of the wrap on external validity. We had construct, then external. Now we have our third type, which is our internal validity. So this is how much in the experiment, in our study, are we sure that the IV, the independent variable, is actually the thing that is causing a change in the DV. And I put cause in italics because we never actually know causation, except in a perfect experiment, which doesn't really exist. But we want to think how much of the variation in one is explaining the variation in the other, that it's not some other variable. These other variables are called confounds. And this is anything that is explaining the variability between the two, the IV and the DV. It's something that differs between the experimental groups other than the independent variable. For instance, I might be doing this stress task, and this is actually a study I did where I brought some people into these Trier stress task, and they had a certain level of stress, and I measured their stress afterwards, and I measured how long it took them to kind of re-regulate. And I did that in just a control condition, nothing else helping them to cope, versus my experimental condition where I had the Trier, but they got to talk with a partner before and after, a loved one, a significant other, who was there to kind of help them prep, help them talk down, say, oh, what did you do right? How are you feeling about it? And I wanted to see how these couples talked. And you might guess that what I found was that the couple, or the experimental condition that had a social support, that had a significant other to talk to, they actually re-regulated a lot better. They had better coping mechanisms because they had someone else to kind of help them to cope. And so I found less stress in that second experimental condition. So I would say there was internal validity that the coping, but what if during my experiment there was a jackhammer going outside of my control condition? Those people who didn't have any social support, not only did they not have social support, but they also had a jackhammer running. It just happened that during the time of the day when I was collecting them, you had a really loud, really obnoxious going right outside the window. Well, that might also hurt your ability to cope. But if I didn't measure it, if I didn't specifically measure it and control for that, I didn't put it into my study, then it is something that is systematically affecting one group and not the other. There's no jackhammer in that social support talking to your significant other condition. It's only in one. So a confound would be that jackhammer. It is something that differs in the experimental group than in my control group, or vice versa, something in my control group that was not in my experimental group. That is specifically not my independent variable. I kind of said this earlier, but the only way you can make a confound not a confound is by measuring it, turning it into an independent variable. And then you can have a little bit more control. So thinking about what might be a confound in any of your studies is a big part of research creation, because if you measure it, then you can control for it. All right, so you've had a lot of math, you've had a lot of terms today. This is a very term-heavy lesson. So we have three types of validity that you need to remember. The first is that construct validity, which is how well you're operationalizing, turning your construct into something you can actually measure. How much does it represent the variable in the real world? Then there's that external validity, which is how much does it generalize to other populations, other situations, that real world comparison versus just feeling like a lab, it's not really real. And then you have your internal validity, which is knowing that the variance in the independent variable is the only thing that's affecting the variance in the dependent variable, that there's no confounds there, or there's very little confounds, there's very little other variable that's affecting things and affecting how you're measuring that variable. So today we talked about constructs and variables. We talked about why variability is so important and ways that researchers measure and statistically account for variability. And then what does it mean for a variable to be valid? Again, those three types of validity. Next week, we're going to talk about types of construct validity, as well as introduce the idea of reliability and how to measure things, different levels of measurement. See you again.